Throughout the 20th and 21st centuries, the third element of the periodic table has found its way into many technologies, some ubiquitous and some obscure. From nuclear reactors to ceramics, batteries to medicines, this element has proven to be of significant importance in the modern economy and in technology. In this video, we will explore that element. We will explore lithium. Hello and welcome to 34 Tauri, the channel where we look at the history of science, technology and discovery. This video is of course on the third element of the periodic table, lithium. It will provide an overview of the element's properties and then move on to how it was discovered and named, and finish with exploring some of its many uses. In its pure form at room temperature, lithium is a soft silvery white metal. As the first element of group 1, and with its preceding elements hydrogen and helium, both being gases at room temperature, lithium has the lowest density of all metals and is the lightest of the solid elements. As with all alkali metals, lithium is very flammable and reacts furiously with water. If left exposed to air, it quickly corrodes to produce a black tarnish. To prevent these reactions, it is normally stored in an inert liquid such as purified kerosene, mineral oil, or an inert gas or vacuum. Lithium is found in two naturally occurring isotopes, lithium-6, which makes up 7.5% of the element's natural abundance, and lithium-7, which makes up the remaining 92.5%. Together, these two isotopes have some of the lowest binding energies per nucleon of all stable nuclides. Because of this instability, lithium is comparatively rare. Even though it is one of the lightest elements, there are at least 25 more abundant in the solar system than it. This is an exception to the trend that lighter elements are more common than heavier ones. While heavier lithium isotopes have been produced, none of them have a half-life over a second. This instability makes the element useful in nuclear physics applications and research. The first lithium mineral was discovered in 1800 by the Brazilian statesman, chemist and poet José Bonifácio de Andrada e Silva. At the time, he was studying in Sweden when he discovered a new mineral on the island of Uto, which he named petalite after the Greek petalon for leaf. 17 years later, samples of petalite from the mine were taken to the lab of Jöns Jacob Berzelius in Sweden. There they were analysed by his protege Johann August Alfredson. Through his experiments, Johann was able to determine the silica and alumina content of the mineral, but he found these only accounted for 96% of the mineral's mass. After more investigations, Johann and Berzelius determined that the missing mass from their calculations must be due to a new element in the sample. Johann found that unlike sodium and potassium, this element forms salt compounds, and that its carbonate and hydroxide variants were less soluble in water. He deduced that the element was an alkali metal lighter than sodium, but that, unlike sodium, it could not be separated into its metallic form by electrolysis with the equipment available at that time. Berzelius gave the alkali metal the name lithium, or lithina, from the Greek word lithos, meaning stone. This was to signify its discovery in a solid mineral as opposed to previous metals like sodium, which was first discovered in blood, or potassium, which was first discovered in plant ashes. Johann also showed that lithium was present in the minerals spodumene and lepidolite. In 1818, the German chemist Christian Gmelin was the first to observe that lithium salts produced a bright crimson flame when cast into a fire. However, he too failed to isolate the metal. It wasn't until 1821 that lithium was finally isolated as a metal. By performing an electrolysis of lithium oxide, the English chemist William Brand was able to produce small amounts of the metal. However, the amounts he obtained were too small to make any meaningful analysis of. To his credit, Brand was also able to describe some pure salts of the element, such as lithium chloride, and he even made some erroneous calculations as to the metal's atomic weight. Experimentation on the electrolysis of lithium compounds continued until 1855, when large quantities of lithium were obtained by the electrolysis of molten lithium chloride. These experiments were carried out by German chemist Robert Bunsen and British chemist Augustus Mathiasen. The procedure was later used by the German company Metallgeschaft in 1923 to produce lithium commercially. At the time, they used a liquid mixture of lithium chloride and potassium chloride, which they then electrolyzed. Lithium does not occur in a pure form in nature. Instead, it is found bonded or dissolved with other elements in rocks, brines, and seawater. In rocks, it only occurs in small amounts in pegmatitic minerals. The most important of these minerals are petalite, spodumene, lepidolite, and amblygonite. While the element makes up only 0.002% of the Earth's crust, the lithium oxide content of these ores can range from 4 to 8.5%. And due to its solubility as an ion, it is present in seawater and the waters of many mineral springs. In seawater, it has a concentration of 0.1 part per million. Historically, lithium and its compounds were produced from rocks such as spodumene, but in the 1990s, mineral springs, brine pools, and brine deposits became the dominant sources of the metal, as they are less cost-intensive than extracting from ores, which requires the input of a lot of energy and the use of acids for leaching. More than half of these brine sources are from Chile, Bolivia, and Argentina, the so-called lithium triangle. In Chile, the brine's lithium concentration is increased by solar evaporation in a series of open-air ponds. First, the brine is pumped up from a natural brine aquifer, called a salar, before being filtered to remove any undissolved solids and deposits in the first of the series of evaporation ponds. Each of these ponds serves to remove contaminants such as potassium, calcium, magnesium, and sulfate, which precipitate out of the solution. Once the concentration of the brine reaches 6%, it is sent to a processing plant, where it is sieved and treated with various chemicals and ions surfaces to remove any remaining contaminants. If desired, the product can then be treated with hydrochloric acid to produce lithium chloride. Lithium chloride may be pumped to a reactive crystallizer if the desired product is lithium carbonate. Lithium carbonate is made from the brine at this point by adding sodium carbonate to lithium chloride. The final solid mass of lithium carbonate is then collected using a filter press or a centrifuge. This process is extremely time-consuming and may take up to 1.5 years. It also requires a significant amount of land with desert conditions for the brine evaporation pools. Many lithium products are made from its carbonate, hydroxide, and chloride forms, but some materials still require the actual metal. To get it, lithium chloride needs to be electrolyzed. To produce the metal, lithium chloride is mixed with potassium chloride before being electrolyzed. The electrolyte contents of a cell are heated so that the salts melt and become a liquid. The lower melting point of this mixture, at around 400 to 420 degrees Celsius, compared to pure lithium chloride at 610 degrees Celsius, reduces the amount of energy required to perform the process. The positively charged anodes of the electrolytic cell are made from graphite, while the negatively charged cathodes are made from steel. since lithium chloride has a lower decomposition voltage than potassium chloride. A voltage is used that is high enough to electrolyze the lithium chloride, but low enough that the potassium chloride is not affected. The lithium alloy forms at the cathode and pulls to the surface of the cell, where it is prevented from coming into contact with the air by a thin coating of electrolyte. At this point, there are still contaminants in it, and it is only 97% pure lithium. The lithium is then ladled from the cell and poured into a mold that is slightly above its melting temperature. From here it is melted again, and the insoluble materials in its molten form float to the surface, or sink to the bottom of a pot and are removed. This remelting step reduces the amount of potassium in the material to less than 100 parts per million. While harder than other alkali metals, lithium is still softer than lead, and it can either be rolled into sheets or drawn into wire. Alternatively, other lithium alloys can be made directly through the electrolysis of molten salts, by mixing lithium chloride with either another metal chloride, or by using cathode materials that interact with the lithium deposit. The metal is also present in seawater, and proposals have been made to extract it using electrodialysis and electrochemical intercalcation. In principle, a membrane of ion-selective cells could collect lithium either by using a concentration gradient or an electric field. Back in 2022, the world was estimated to have used 134,000 tons of lithium per year. 80% of that was consumed by lithium battery production. 7% was used in making ceramics and glassware. 4% was used in making lubricating grease, and another 2% was used in continuous cast mold fluxes. The remaining 7% was used for a variety of different applications, including as an additive in improving the qualities of alloys, nuclear physics research and nuclear fuel production, hydrogen storage, removing impurities in the refining of metals, reducing the melting temperature in aluminium smelters, dehydrating airflows in air conditioning units, oxygen candles, and in the treatment of manic depression. Today, most lithium is used to make batteries for use in mobile devices, such as mobile phones, electric vehicles, digital cameras, and laptops. Because of the element's high electrode potential, it can be used in both battery electrolytes and the electrodes themselves. Furthermore, lithium's low atomic mass gives it a high charge and power-to-weight ratio. Typically, they come in two types. Lithium metal batteries are disposable and use anodes made from lithium or one of its compounds. Despite their higher cost, they have a higher charge density than pre-existing batteries and lithium-ion batteries. Lithium-ion batteries, on the other hand, use a lithium salt dissolved in an organic solvent. These batteries are rechargeable while retaining the high energy density. Lithium oxide is regularly used to reduce the melting point and viscosity of silica while it is being processed. This leads to glazes with better physical properties, such as low coefficients of thermal expansion, which can be particularly useful in making ovenware. Lithium carbonate is often used as the feedstock for this because it converts to an oxide upon heating. Lithium hydroxide is a strong base, and when it's heated with an oil, a soap is produced. These soaps have the ability to make oils thicker, and due to a higher melting point, they are used to produce high-temperature lubricating greases. Being less corrosive than calcium soaps also makes them more desirable than regular soaps for lubricating machines. In fact, lithium's first use in industry was in high-temperature greases for aircraft engines and similar roles during the Second World War. Lithium carbonate is used in continuous casting as a mold flux. Continuous casting involves shaping a constant stream of metal before it has solidified. The mold flux lubricates the surface between the steel cast and the mold, preventing them from sticking together while also providing a thermal barrier between the two, which prevents the casting from cooling too quickly. Lithium can be added to other metals to produce alloys, which can have different physical properties to the main metal they are made from. Examples of their use include aluminium-lithium alloys, which are used to make high-speed trains, aerospace vehicles, and bicycle frames, and magnesium-lithium alloys, which are used to make armor plating. It can also be alloyed with cadmium, manganese, or copper to make low-density, high-performance aircraft components. The demand for lithium increased significantly during the Cold War. When irradiated with neutrons, the isotopes lithium-6 and lithium-7 produce tritium and the fusion fuel lithium deuteriide. This material was used in staged thermonuclear weapons at that time period. However, weapons are not the only use for lithium in the realm of nuclear physics. The element is also used in nuclear reactors as an anti-corrosive agent. In pressurized water reactors, the pH of the coolant is kept high to minimize the pitting and corrosion of the metals used in the hydraulic system. For this reason, lithium-7 hydroxide monohydrate is often used as an alkalizing additive to reactor coolants. Lithium-7 is used because it has a low nuclear cross-section, which means that it is less likely to absorb neutrons coming out of a reactor core, which would then cause the isotope to decay into tritium. Lithium can also be used as a flux in the refining of other metals to scavenge a range of non-metallic impurities from the molten metal. These impurities can include nitrogen, oxygen, hydrogen, sulfur, carbon, and the halogens. As a flux, it can also lower the melting point of metal ores and their wastes, making them easier and cheaper to process and extract. As lithium chloride, it is sometimes added to the cryolite in the Hall-Héroult process to both lower the electrolyte's melting temperature and improve its conductivity. This reduces the energy required to smelt aluminium and hence makes the process cheaper. Metallic lithium is also used to make lithium hydride, a grey crystalline solid produced by the direct combination of lithium with hydrogen at high temperatures. When this compound is exposed to water, it instantly decomposes to produce hydrogen, and so lithium hydride is used as a method of storing hydrogen fuel. Lithium bromide and lithium chloride both absorb aerial moisture over a range of temperatures. Because of this hygroscopic ability, they are used for desiccating gas streams, as well as being used in air conditioning units, large refrigerators, and industrial drying systems. Due to its comparatively low weight, lithium hydroxide is commonly used for removing carbon dioxide from air supplies in closed atmospheric systems, such as those found on submarines and aircraft. The compound absorbs carbon dioxide from the air to produce the solid lithium carbonate. Meanwhile, lithium peroxide can be used to produce oxygen. To do this, it has to be combined with carbon dioxide in the presence of water vapor and produces lithium carbonate as a byproduct. However, this is not the only way lithium peroxide can be used to produce oxygen. In oxygen candles, it is combined with lithium perchlorate, which when ignited slowly smolders to release oxygen. Oxygen candles are used to provide a breathable atmosphere in submarines, some spacecraft, and mines. In 1949, the Australian psychiatrist John Cade popularised the use of lithium in treating mania, a mental condition marked by periods of excessive excitement and euphoria. In 1954, lithium carbonate was shown to be effective in treating patients with manic depression, and by the latter half of the 20th century, its use took off throughout Europe and the United States. While its action on the brain is still not fully understood, the compound has been identified as the active element in these drugs. Today it is the primary drug used in the treatment of patients with manic depression. Anyway, that's all for this video. Thank you for watching. Links to all the sources used can be found in both the credits and down in the description. As with all video channels, please feel free to like, comment, share and subscribe, and until next time, have a good evening.